I actually advance with? I'm sorry, I rushed in myself late.
You've got this fancy iPod doodad,
Okay.
so push the little
All
bullseye.
right.
And you can either hit the arrow or you can sweep it.
Awesome. Okay. Good. Now I know that, so now I can teach you guys that later. All right. So I freely admit I have way too much stuff in here for 12 minutes, so I'm going to rush right into this guy here. Okay. So first of all, just to get the big picture, the decadal survey, we really want to know, where is the ice that we're viewing in the solar system coming from, and what is this telling us about the evolution of the inner solar system that should have formed dry? Okay. And now we have. Sorry, I have an echo of myself here. All right. Okay. So this begs two big questions: is how and when did these volatiles get to the inner solar system? We're observing them on planets like Mercury, on the Moon. Where did they come from, and when did they get there? Okay, so I'm going to go briefly through an overview of some of the tools I use, some of the discoveries of ice on the inner planets and the inner solar system, and then I'll talk about the Moon and Mercury. And then the main thing I want to talk about is a new paper I'm working on Lunar Obliquity. I got reviews back yesterday, so if any reviewers are in the audience, I didn't look at them purposely because I don't want to know before I give the talk what the reviewers canned. So anyway, here we have the polar. There is an echo about 1 second after yourself that you hear here. Okay.
Oh, it's probably the iPad talking back to you from the WebEx.
Okay.
Can we turn that volume off on that?
All right. Well, anyway, we'll figure out maybe before the next speaker. Okay, so essentially what I do is a lot of thermal modeling. We look at some surface temperature conditions, look for where ice would be stable. I could go into all of that. But essentially, there's an animation that didn't go through. But essentially, we can do this modeling to figure out what depths ice will be stable under the surface. And I can go into details about that at a later time. We applied this successfully to the Moon and Mercury to predict where ice would be. And the shocking thing to everyone was that Mercury seems to fit the models. All right, we find signs of water ice and subsurface ice pretty much everywhere that we see it with the messenger probe. But on the Moon, we're having a different story altogether. So I'm going to go through one possible explanation of why we have a difference here. Okay, so I'm using a model that we built associated with the Lunar Reconnaissance Orbiter. What we've done with this model, right, it very successfully predicted the temperatures of the Moon. Here's the data from Diviner. Here's a model. Here's nighttime versions of the same thing. So we're doing pretty accurately. So we're saying we can trust this model to predict temperatures, within reason. And so what this means is then we can also use it to look for subsurface where subsurface ice will be stable. This is work from Norbert Schonghofer, did all these models of ice stability as a function of depth. And you can see that if you bury ice by something like 10, 20 centimeters, you're going to get a large a slowing of your loss to space. Okay, and so here's the map that we get for ice stability. Sorry, this is really distracting. Okay. Anyway. Yeah, it's okay. Don't worry. Okay, and so essentially we want to compare that to the neutron data. And so we saw on the earlier slide that we had high neutron deposits here in Cabeus crater, and over here, and in Rich's talk we saw that. Okay, so what I want to look at is how the orbital histories of these bodies come into play. So Mercury, we can run through really quickly. Its main variation is its eccentricity. Mercury hasn't gone through any obliquity shifts like we're used to thinking on Mars. So this eccentricity is the main control over ice stability at its poles. We can look at this little box location here. Oh, Sorry, I'm having so many technical difficulties here. Okay, and so here you could see two extremes of. All I'm doing is pushing the button. Okay. Anyway, the moral of that story is that Mercury's main change for ice stability is the eccentricity variations, and there's not a whole lot of change. What those two pictures showed is that 0.1 degree or 0.1 eccentricity and 0.3 eccentricity, we have pretty much the same map of subsurface ice stability. It's going to change by a few centimeters, but Mercury, the conditions don't really change. On the moon, we have something more extreme. We have a more extreme change in the obliquity over its history due to locking in a Cassini state, which I've presented here before, and I can go into details about that to anyone. But the result of that is that when you model the obliquity history of the moon, you get a picture like this. When the moon was back at around 30th radii semi-major axis, it was flipped on its side. Okay, this is due to tidal dissipation within the moon. And any body trapped in Cassini state, and Mercury is essentially in a Cassini state, many of the moons of Jupiter are in a Cassini state. It's actually a common occurrence, but the weird thing that the moon has had is that it's tidally evolved out. And so its precession rates have changed and caused it to go through this large obliquity transition. So what I want to then look at is different points along that obliquity transition, which we don't really know when it happened exactly in time, because we don't know how fast the moon is moving out in its orbit, to see what the temperature changes on the moon have been as a function of obliquity changes. All right, so we're going back in time now. So here's sort of average temperatures from our model today. We match these to Diviner. We trust them. So the model seems to be working well. Let's crank that model back to 4 degrees, 8 degrees, 12 degrees, okay? And you can see cold traps didn't used to exist, all right? And these things are happening in the last roughly 1.5 to 2 billion years is probably when we were back around 12 degrees. This is declination, is a combination of obliquity and orbital inclination. So then we can then apply these same ice maps to look at how was ice stable in the past on the moon. And so we can go back, and what you see here is that even when you go to 4 degrees obliquity, we get a big change in where ice would be stable. So the white areas are where we have surface ice stability. And so you can see we're losing the rims of these large, pretty big craters. Cabeus loses its surface ice stability. Go back even further. And one of the neatest objects in this is that Shackleton crater that we just talked about in Rich's talk is actually the oldest cold trap on the moon. And as far back we can go in obliquity, it stays cold. So that might be an interesting and significant thing. Another thing to look at about ice stability is actually not the stability of ice, but the mobility of ice. So essentially, you're going to be driven down. If you're a water molecule landing on the surface, you're going to be driven down by the temperature gradient. And the stronger that temperature gradient is, the stronger vapor gradient you get, or saturation vapor gradient you get, as long as you're saturated, which doesn't take many molecules at this temperature. Okay, and then you can drive ice downward. And essentially, this will become stronger the larger this gradient is. And so one thing you might want to map is, let's look for places where you could capture ice on the surface, and then where they would pump most efficiently into the subsurface. So now we can look at the moon today, and what you see here is, so blue is good pumping, all right? And Norbert Troghofer and Odette Aronson just wrote a paper about this as well. And this is just another way of calculating that same thing. So what we see here is all the blue areas are areas where you could imagine that if a water molecule landed, it would pump down into the surface very efficiently. All the red areas are where a water molecule would land on the surface, just stay there, okay? And then Lyman alpha light might eat away at it, or cosmic rays, or whatever mechanism of getting rid of surface ice you could come up with. These are all subject to that. We can go back further in time, and you can see that certain areas will change how well they ooh, I'm bouncing around a little. They were able to pump ice. And so you see as you go back to 4 degrees or 8 degrees, these big craters that we're used to, Hayworth and Faustini and Shoemaker, are all good ice pumps. So what I want you to look at is this plot here is sort of a summary of all that, of looking at a few distinct craters in this model. And you can see Shackleton, right? Shackleton has always been cold and has been a good ice pump for most of its history. So we go back, so this is back in time here, back in higher angle. And what I've drawn on here is from Dana Hurley's models. We have the gardening rate, that how fast gardening would overturn the material. So essentially, if this rate of ice mobility from temperature is above that line, you should imagine that ice mobility will dominate the movement of ice through the soil. If it's below that line, then gardening will dominate that. And so essentially, what I'm conjecturing is that if you're above that line, okay, then if you have any water molecules delivered to the moon, they're going to stick somewhere in the near surface. And then as soon as you cool below that line, you're subject to gardening, and anything in the near surface would go away. And so what's interesting here is that the L-Cross site is one of the most recent places to have this high ice mobility and then have gone into this deep cold freeze. Okay? And so that happened maybe between 2 and 3 degrees tilt of the moon. And so what you have there is a ability of that area to collect a lot of ice efficiently, thermally, and then it shut off recently. And then for the last, however many millions of years that is, maybe that's 200 million years or something, when we're back at 3 degrees tilt, you've been gardening the surface. And places like the Shoemaker and Faustini and Hayworth went into that same freeze much earlier, and so they've been gardened more. And so that might explain why we get near superficial ice in some of these places like the L-Cross impact, but we don't seem to see them as shallow in these other large craters. So that was just a way of emphasizing why Cabeus has this strong neutron depletion. So let me just end there because I'm running over time, and I don't want to run over time on my own session. Okay. Yeah, does anyone have questions?
Okay, so we have about 2 minutes for questions. John?
Is there any way we could try to figure out this echo so the next person's not stuck with it? Sorry about that.
The echo is remarkable. Okay, so let's start with John, and then we'll go to Dana. And identify yourself for the people on WebEx.
Goddard. My question is about the Mercury side of this. You have a pretty good story for the moon, but the argument seems to be that the difference between moon and Mercury is that over geological times, the obliquity of the moon's orbit changed. But that means that the superficial ice on Mercury existed over geological times, and that probably is not possible due to the radiation destroying superficial ice. Is that?
Yeah.
Have any comments on that?
So to keep an active surface frost, you need some constant way of resupplying it. And so there's lots of mechanisms people have looked at. They're resupplying, be it solar wind or very recent comet impact. The fact that you have blocks of water ice apparently below the surface, some of that should be desiccating, coming back up to the surface. Can you imagine the lowest latitude ones might be desiccating, and those molecules might be hopping to the coldest places. So the surface frost on Mercury has to be being resupplied from somewhere to maintain it.
Okay, then we have time for a quick question.
So this is Dana Hurley from APL. Are you saying that the Cabeus one, it frozen more recently than the others, and so the others are buried more deeply, or?
Yeah, the other craters could have collected more ice in the past, but gardening has taken over for the last, half billion years or longer in Faustini and Hayworth and Shoemaker. And so, yeah, so as you've modeled, that should erode most of the ice in the top meter and could explain why we don't see much in the neutron in those areas. Is that, the last time they were really good ice collectors, the ice wasn't long enough ago that we're not seeing it anymore. So from looking at the gardening rate and looking at the percentages you see in Cabeus, for instance, you might be able to give a prediction of how long ago something like the comet that we think hit Mercury recently hit the moon.
Okay, we're going to have to wrap it up there.
Okay,
thank you
thank
very
you.
much. Thank our speaker. All right, our next talk is officially Dave Glenar, but I see that it's not actually